All right, cool.
All right. Well, welcome everyone. It is my my pleasure to introduce our new professor in our department, Ángel Adames-Corraliza. Ángel very recently joined us, and unfortunately, he's only been with us through this COVID period. So soon you will be able to run into him all the time in the hallways. But until then, I'm glad that you're giving a talk on Ángel so that everybody can get to know you better until we can all talk in person, right? So Ángel has many research interests, largely in the tropics. He has done very impressive work in furthering our understanding of the MJO. This is where I have seen a lot of Ángel's name quite a bit. You can't really research the MJO without running into an Ángel paper. He's also done a lot of work with tropical wave dynamics and tropical thermodynamics. He only fairly recently, relatively recently, received his PhD in 2016 from the University of Washington. But even though his early career, he has a lot of accomplishments that are definitely worth mentioning. He has numerous publications, book chapters. He's already been a keynote speaker for multiple different conferences. He is the 2019 National Academy of Sciences Cobley Fellow, and I'm not sure if I'm saying that right. He's also the 2018 recipient of the James R. Holton Award, which is an AGU award for outstanding research and accomplishments of an early career scientist in the atmospheric sciences, which is not an easy award to get. So it is certainly great to have you join our department, Ángel. And for those of you who are Spanish speaking or are hoping to become Spanish speaking, Ángel does have a podcast which we were just talking about, which is called Tiempo, Clima y Tierra, which means weather, climate, and earth, which is fully in Spanish, and he has a lot of international scientists who come on his podcast. Ángel is from Puerto Rico, so he does a lot of outreach in Spanish. So thank you, Ángel, again for giving us a talk, and I will turn it over to you.
Thank you, Stephanie, for the introduction, and especially for pronouncing my last name properly. This always makes me very happy. You know, it's not an easy last name to pronounce, actually. So thank you for that. It is my pleasure to be here with all of you today. I hope we've all got some time to rest over the weekend and are ready to rumble with some atmospheric sciences today. Like Stephanie said, I'm like the newest professor here, and I haven't had an opportunity to really get to know a lot of you guys here. So hopefully this is a bit of an introduction. I was hoping to have this talk so I can give you a little bit of an idea of what I've been doing and my research group has been doing, and then, you know, kind of just bring a little bit of the research out there. So if people want to collaborate or talk, do some science, nerding around, always happy to do all of these things with you guys. If you are interested in stuff, my email's here at the bottom. So if you want to like send me an email and want to chat about science, always happy to do so. Okay, so today we're going to talk about a simple model that I've been kind of working on and off for the last couple of years. This is me being truly honest. Like, this is kind of like an extension of my postdoc work. I just didn't have time to do it. So I just slowly and very, very, very slowly kind of went and did it. But it's finally a publication that's been in review. We're going to talk about how a simple quasi-geostrophic model changes when you add water vapor and convection to it. So that's going to be the main topic of today. And I'm going to go on and talk a little bit about the justification as to why we're going to do this. All right. So if you look at a picture of the tropics, like the one that is shown here in the image, here's an image from Africa from this year. You see that there's a lot of tropical disturbances. They're quite ubiquitous in the tropical atmosphere. If you examine these very carefully or look at one of these model outputs, you'll notice that a lot of these disturbances are fairly rotational. So they swirl around like the TCs that are developing in this picture. And they are quite important. actually. They're fairly important to the hydrological cycle. They can also lead to tropical cyclone formation. So there are more than plenty of reasons why we want to examine these disturbances. All right. So there's two systems that we want to pay a particular focus today in this talk. One of them are the African easterly waves, which are pictured here. They occur over Africa, and they're quite rotational, as you see here. And the other one are the monsoon low pressure systems that are a set of systems that occur mostly over the Bay of Bengal to the east of India. And the reason why we want to focus on these two systems is because they exist in a mean state that's quite unique when it comes to the tropics. And I'll discuss a little bit of why this mean state is important and why we want to understand these systems in the following slides. Okay, so what makes these regions unique? So if you look at this picture, you'll see that Africa, you see that these systems are occurring over Africa. You can kind of not tell very clearly, but there's the Atlantic Ocean here in the dark, and then Africa's over here. And you can see the easterly waves kind of in this in-between region. And then similarly, you see that you have the Indian subcontinent, Asia here to the north, and then kind of open ocean to the south. And what happens when you have this kind of configuration is that you get a temperature gradient that is poleward. So here's a cross-section of the South Asian monsoon. The zonal winds are shown in contours. So westerly is the solid contour, easterly is in the dotted contour. And you can see that, one, here's the 0-degree latitude, so here's the equator. So we're going north in this direction here. And you see that in South Asia, you get a westerly jet at about 15 degrees of latitude. And as you go up in height, so here's the pressure, and you go up in height, you'll see that it turns into easterly. So you have a wind shear, you have a vertical wind shear in these regions. And the wind shear is easterly because it goes from westerly to easterly as you go up in height. And that is in thermal wind balance generally with the poleward temperature gradient. And this temperature gradient exists both over Africa and over South Asia. And this is kind of unique. There are other regions of the tropics that you see this, but not to the same magnitude and extent that you see it in these both Africa and South Asia. So why are these regions so important? So in the mid-latitudes, you do have a temperature gradient. It's in the reverse direction. It is equatorward. So you're in the mid-latitudes, you just get colder as you go towards the poles. And we know, if you've taken GFD or if you've taken a synoptic meteorology class or, are just generally savvy about meteorology, you know that these types of mean states are conducive to baroclinic instability. Baroclinic instability is the main instability that leads to the development of storm systems in the mid-latitudes. So they're quite ubiquitous in the mid-latitudes, and we have documented this instability very well. I'm not going to show you the nitty-gritty of baroclinic instability, but we'll tell you one of the main features of it. So when you have a westerly shear, like you see here in the image, which is just the wind just becoming more westerly with height, the regions where baroclinic instability happen are usually characterized by a low that tilts westward with height. So you have a low at the surface, and then you have a low higher up in the troposphere. Usually in observations, you have a surface low and then a trough at higher levels shifted to the west. So this spacing is very characteristic of baroclinic instability. And for a long time, I'm talking about the mid-latitudes right now, so here's in the picture, it was thought that these regions in the tropics were kind of analogous to these mid-latitude regions, but they would be in characteristic for the reverse kind of temperature gradient. All right. So in baroclinic instability in the mid-latitudes, you have a westward tilt with height, like you see here on the right. But then in the tropics, where the temperature gradient is of the reverse direction, you could still have baroclinic instability, but the tilt will be in the opposite direction. So you would just have an eastward tilt with height. All right. And so here we're comparing the two of them, and again, they're in the reverse direction of the tilt. And another thing that is important to note is that because we're in the tropics and we're talking about regions that are monsoonal, that are very humid, you can actually have very deep convection occurring with these regions. So you can also have a modification from convection that can also help strengthen the baroclinic instability. So here on the left is what we would think would happen over both Africa and South Asia. So would you have a baroclinic instability, or would you have some kind of convection near or to the left of the low, and then the tilt will be eastward with height? All right. So I would not be giving this talk if we knew that this was indeed what happened and we would observe this in these systems. So what we see is instead that, for example, easterly waves, and I'm going to show here the PV structure. You can ignore the contours, just focus on the shading, which is the potential vorticity. You see that you can use the potential vorticity as like a proxy of the circulation. By the way, you can see that there's no clear tilt in these systems. So here's, again, the pressure. So this is increasing height. And you see that there may be some eastward tilt with height near the surface, but then as you go into the mid and upper troposphere, you don't really see this kind of tilt. And instead, you see kind of something that is some kind of combination of upright versus kind of like a westward tilt, which is the tilt in the opposite direction of what it should be showing, and then a reversal in the upper troposphere, okay? So an easterly wave in the African region does not have the characteristics consistent with baroclinic instability. And again, on the left, I'm repeating that schematic from the previous slide just for you to compare and see that the low is just really not having that kind of structure that you would expect. But this paper, by the way, is from Russell and Nair, 2020. So their paper was questions the importance of baroclinic instability in African easterly waves. So let's think now about monsoon depressions or monsoon low pressure systems. So let's think about these. So again, the color is the potential vorticity, and now we're looking at monsoon low pressure systems. So now we're moving to South Asia. So again, you have here.
To interrupt, John Martin had raised his hand. He had a question quick.
Okay, yeah.
Yeah, sorry, Ángel. On the prior diagram, maybe I'm just being misled, but it looks to me like there's an axis of tilts to the west with height in both of those, or maximum and a minimum that tilts to the west with height by about 5 or so degrees from 800 to 400 millibars. Is that just, am I missing something?
Yeah, it's just, it is tilting, but it's tilting in the wrong direction with respect to the local shear. Well, the shear here varies a lot.
Okay. Yeah. Okay, certainly I agree with that. Oh, I thought you had said it wasn't tilting. Sorry.
Yeah, it's just not in the right direction. Yeah.
Okay.
Right, cool. Moving on. So let's go to the monsoon low pressure systems over Asia. So even more so than here again, we're looking at the shading is the potential vorticity. We're going to ignore the contours for now. So if you just focus on the shading and compare it to what you would see theoretically from baroclinic instability, you notice that the first thing is that you don't really see any clear tilt. Maybe there's a little bit, but in the opposite direction. But overall, the structure is pretty upright. It's a fairly upright structure. It doesn't have a lot of tilt. So again, similarly to the African easterly waves that we saw in the previous slide, we are again seeing a structure that is just generally not consistent with baroclinic instability. So that leaves an open question. It does seem like these systems are not driven by baroclinic instability, or at least based on the structures that we are seeing. Now I'm going to add some complexity to the problem. So Adames and Ming in 2018 looked at simulated monsoon depressions from the GFDL AM4 model. Here's the geopotential in contours in the top diagram, and the meridional wind is shown as shading. But I want to use this top panel to contrast the bottom panel, because this is where things get really intriguing. So if you look at the bottom panel, you'll see the vertical velocity is in dashed, the moisture is in dotted, and then the precipitation anomalies are the solid line. And what we see here is that the vertical velocity does not correspond exactly with the precipitation. It's shifted to the west. Instead, the precipitation is more in phase with the moisture anomaly. So it seems that it's raining where it's humid, not where the vertical velocity is the maximum. Okay, and what this implies is that the large-scale lifting is not necessarily corresponding with the precipitation. You have a lifting that's due to precipitation, but one that is adiabatic. It's not associated with heating, and that's actually shifted to the west of it. So this and then implies that there is a mechanism that's causing the lifting that is not necessarily causing the precipitation. The precipitation might be driven by thermodynamics. It's humid, so you're having less dilution, or maybe there's more cape in the region where it's more humid, but not necessarily where you have all the lifting. Okay, so what are the questions that are leaving to today? So all things are indicating that baroclinic instability is not the mechanism that's leading to the growth of these systems. So that leaves the open question that if it's not baroclinic instability, then what is? So Adames and Ming, and this is a different paper, suggested that monsoon lows could instead grow from something that they called moisture-vortex instability. And in moisture-vortex instability, the system grows through feedbacks that involve water vapor, convection, and the circulation, similar to the diagram that you see here on the left. So you can have large-scale lifting, moistening the environment, and then that moistening leads to convection, close to in phase to the circuit like you see here, which then intensifies the vortex. And I'm going to go into more towards the end of the talk. But the end result is that this is not baroclinic instability, and it's very different in nature. However, they did not actually take into account the mean state of the Asian monsoon nor the African monsoon. They kind of like did it super idealized, just had convection and circulation, and then just showed that this instability can happen. So that leads to the questions today. If we look at a simple model, with a two-layer model that has vertical wind shear, a thermal wind, make it as simple as possible. So we're just going to make a QG, and we'll talk a little bit about that in the next few slides. And if you just run that model, or if you just solve that model, so solve for instabilities, do new instabilities arise from these interactions, from interactions between the circulation, deep convection, strong vertical wind shear, and moisture, right? And if instabilities arise, then how are those instability like? Number two is, it seems that baroclinic instability does not occur in the South Asian and African monsoons. And why? So what are the mechanisms that are driving baroclinic instability to weaken or not play a role in these systems? So those are the questions that we are trying to answer here. Okay, so what is the model setup? So this model that we're discussing today is essentially the same model that's discussed in Chapter 7 of Holton and Hakem, but with prognostic moisture. So it's just a two-layer model. You just have an upper troposphere that is bounded between 500 and 0 hectopascals. And you have a bottom layer that is bounded between the surface at 1,000 hectopascals and then the mid-troposphere at 500 again. And then all the moisture is just assumed to be in the bottom layer, in what we're going to refer to as the bottom layer. The moisture is going to be then the addition. The Holton and Hakem model was dry. This is not going to be a dry model. We're just going to have a prognostic moisture equation, which is going to be the big departure from this old model. Everything else is going to be the same. And then you have the top layer that is going to be dry. Okay. And again, I'm going to add that there's no vertical velocity at the top of the bottom. So there's a rigid lid boundary condition, and there is going to be communication between the two layers by a vertical velocity and the in-between here at the 500 hectopascal. So there's going to be some communication between the layers. Okay. All right. So I just mentioned the configuration. There's going to be a prognostic moisture equation, and in order to close the system of equations, we need some kind of parameterization of convection. We can use multiple things, but we're just going to go for like a very simple convection, which is the Q. It's just going to be proportional to the lower tropospheric water vapor. So Q3 here is just the moisture in this kind of like lower free tropospheric layer here, 750 hectopascals. And you're just going to like, essentially, this is like a convective relaxation scheme. So essentially, the convection is just going to dry the troposphere. You just have a humidity anomaly, and the convection is just going to eliminate it. We're going to assume that our mean state is humid, because otherwise, like, no new insights are going to be obtained by just doing a dry state. All the new stuff is going to come from the humidity. Our reference latitude is going to be 16 degrees north. And these are going to be our main equations. We're going to have an equation for the stream function, both in the upper and in the lower troposphere. You're going to have a thermodynamic equation for the mid-troposphere. You're going to have a moisture equation for the lower troposphere, and then you're going to have a diagnostic equation for the diabatic heating, which is going to be the convection. And essentially what the convection scheme is telling you is that, here is some kind of like the line here is some kind of moisture. Say that there's some kind of moisture maximum here, you're just going to have your cloud and your moisture maximum. And then the convection, the maximum vertical velocity is going to be right here in this middle line right there. All right, cool. So a few things, a few justifications for the model. If you do an analysis of the Rossby number for African easterly waves and then the South Asian monsoon, usually for the QG approximation to be accurate, the Rossby number needs to be smaller, much smaller than 1. We find that the Rossby number is about 0.25 in Africa and about 0.12 over South Asia. So the QG approximation is quite good for monsoon low pressure systems. It is qualitatively okay for African easterly waves, but is not super accurate. So take the results here qualitatively, but don't just know that they're not going to be super accurate for these waves. But they are quite good for monsoon low pressure systems. I'm going to argue that even though they're not super accurate for African easterly waves, they can still be insightful. So that's why we're still kind of extend some kind of conclusion to them anyways. All right, so I'm not going to go through the details of the derivation. I'm going to show you the land equations there, but what I'm going to tell you is that you're going to combine all the equations into an equation for the barotropic vorticity, which is just the circulation has the same sign in the two layers. So you're just going to have an equation for barotropic vorticity. You're going to have an equation for baroclinic potential vorticity. So this has a temperature anomaly, and the high and the low have you have opposite signs, and the upper and lower layer. And then the new thing that is going to be coming into play in this study is going to be this moist enthalpy equation. And the moist enthalpy here is going to be in PV units. So I'm just going to change it to PV units, but just know that this is moist enthalpy, same as moist static energy for the purposes of this presentation. And this is just the sum of moisture and temperature together. So this is some kind of like energy. All right. So if you express these equations, you're going to get to the next set of equations. And if you don't want to look at them, it's okay. I'm just going to give you two conclusions. So you're just going to have some terms that are going to be in the blue box. Those are the same equations as in Holton and Haycomb. This is just the barotropic vorticity equation. It's just driven by vorticity advection and advection of baroclinic vorticity by the thermal wind. You have your dry PV equation, which just has three terms. Has again advection of planetary vorticity, advection of temperature by the anomalous wind, and then again the thermal wind term here with advection of vorticity by the thermal wind. These are all the equations that appear in baroclinic instability in Holton and Haycomb. You can just go and read it up. So I'm not going to discuss them a lot because what really matters for the stock is going to be the next equation and then this last term here. So this last term that's in green in the baroclinic PV equation is actually vortex stretching from convection. So it's just vorticity generation from convection, PV generation. And then this last equation here is the moist static energy or moist enthalpy equation, and all these terms are just advection terms. So this is like moisture advection by the anomalous wind. This is moist enthalpy advection by the barotropic wind. So the barotropic one again has the same sign. The other one has the opposite sign. So just so you keep them in mind. This third term is actually advection of the moisture or precipitation anomalies by the thermal wind. So the thermal wind can just advect your moisture anomalies. And then this last term here is actually moist static energy advection by the convection. So the convection can just move the moist static energy upward. And if none of this makes sense to you, it's okay. This is in fact a daunting set of equations. This is kind of like GFD and thermal. All of that can bang together into something that might be quite intimidating looking. It's totally okay. I'm not going to show any more equations as complicated as this. I just showed this for completeness. So I'm not going to be going into that much detail after this. I'm going to just show you what the main results are.
All right. Ángel, Dan has a question.
Oh, yeah. Yeah.
Hi, Ángel. So in this, I'm noticing the stretching term, the F0 stretching term. Or do you, in the vorticity equation, do you take into account the variation in the Coriolis parameter for that term? I think in mid latitudes you don't, but in the tropics you do.
So this is far away enough that you can have F0 and then beta, and it's okay. It does work okay. But yeah, it is far away enough from the equator that you can do this. But
even at 16 north.
Yeah. Okay. Yeah. I hear another question. Is that a question?
Yeah.
Yeah,
Ángel, this is Brad. I another point of clarification. It's the same stretching term.
Mm-hmm.
I've always thought that in terms of generating potential vorticity, it's the vertical gradient of diabatic heating. This is related to convection. Is it somehow related to a vertical gradient?
It is, but because this is a two-layer model, the gradient doesn't appear explicitly. So essentially, this corresponds to like heating in the mid layer So essentially, it's kind of like it's telling you that you just have anticyclonic stuff happening, generating in the upper layer, and then cyclonic in the lower layer. So that's just, normally in the stratified layer, you would have a gradient, but because this is a two-layer system, it doesn't show up.
Okay, but it's similar to that.
Yeah, it's essentially physically same interpretation.
Thank you.
Sure. Any other questions? Okay, let's move on. So yeah, so that was a pretty long set of equations. There's a lot going on in there. It's okay if it didn't quite make a lot of sense. What we're gonna try to elucidate today is what the behavior of these equations look like when you solve them from a linear sense. So what we're gonna be looking at is specifically at wave solutions, and wave solutions tend to have the form of eik minus I omega t, where I is just, the imaginary number, so the square root of -1. K is what we refer to as the sonal wave number, so it's just 2 pi divided over the wavelength, and omega is just 2 pi divided over the time scale, so that's the frequency. We're going to be looking at wave solutions, kind of like this animation that we see on the left, where you have some kind of propagating wave with some characteristics. So that's going to be the focus of today. And even though this formula looks pretty innocent, there's actually a lot of complexity in that, and I'm going to explain that now. So we want to know specifically the frequency as a function of the wave number. So we want to know omega as some kind of function of k. And this is known as the dispersion relationship. And that just tells you that the dispersion relationship will just tell you the behavior of this wave that you see, for example, on the left. Right? And it's important to know that this omega can be complex. It's not going to be not necessarily going to be a real number. It's going to have a real component, which tells you the propagation of the wave, and then it has an imaginary component that tells you the growth and decay. And for the purposes of this talk, we are really interested in this imaginary component, which just tells you if a wave is stable or unstable. And in order to make this discussion as simple as possible, we're going to look at some limiting cases. We're not going to look at the full solution per se, because the equations are pretty complicated and there's a lot going on. So what we're going to do first is that we're going to analyze the case when the convective adjustment is actually close to 0. So we're just going to assume that tau c is exactly equal to 0. And in this limit, there's no moisture, because moisture is actually contingent of having this being non-zero. And in this case, we're just going to have that convection is just going to be simply diagnosed from the large-scale forcing. So this pink arrow that you see on the right, you can think about this as the large-scale lifting, and then the teal-colored arrow is going to be the convective lifting. So we're just going to assume that these two things are going to happen exactly in the same place. So what do we get when we get that system of equations that we saw previously, and then just solve it assuming that there's no convective adjustment? So everything's just going to be diagnosed from the large scale. So this is going to be our solution. On the y-axis is the magnitude of the thermal wind. So this is going to be the difference between the upper and the lower troposphere wind shear. So this is going to be the strength of the wind shear. And then the sonal wave number is in the bottom layer. Again, the bigger the wave number, the smaller the scale of the wave is, because it's inversely proportional to the wavelength. And I'm going to have you please ignore the contours. Let's just focus on the shading. So we see that between wave numbers 5 and 10, as you increase the wind shear in either direction, so the negative numbers are going to be easterly shear, and the positive numbers are going to be westerly shear. So the little diagrams are going to tell you always the direction of the shear, and there's a bunch of them going to be shown in the next few slides. So we see that there's essentially growth as red. Growth as red. It just tells you that there's growth only at wave numbers 5 and 10. And this is actually the growth rate that you would expect to see from baroclinic instability in this region in particular. It is enhanced by convection. If you want to know the details, you can ask me afterwards. And if you take, for example, let's just take this case down here in the easterly shear, and let's take this really red spot near 20 meters per second and check what the horizontal structure of the wave is. So let's take wave number 8, so somewhere down here, and look at the horizontal structure of the wave. So we get this diagram to the right. Here's the upper levels at A, and the mid levels are at B, and then the low levels are in C. The stream function, so essentially the geopotential or the pressure, is the contours, with the dotted dash contours are going to be the low pressure, and the solid contours are the high pressure. And then you see that the divergence is going to be the shading, and in the mid panel, the precipitation is going to be the shading. So you see, the first thing that you will notice is that you have a low pressure here at the surface, and you have this tilt with height, eastward tilt with height. And that tells you already that we're looking at baroclinic instability here. You have this tilt. And you see convergence on the surface, precipitation, and divergence at the upper level. Again, is shifted to the west of the low level pressure center. So we can conclude that when tau c, so when you don't have any convective adjustment, no moisture, just large scale lifting and convection, we get baroclinic instability. All right, so far so good. We found baroclinic instability. So we're now gonna analyze a second approximation. And we're gonna get this second approximation by assuming that the convective adjustment is small but not zero. So that means that convection responds very quickly to a moisture anomaly. Now we have moisture. So now we're gonna talk about the case when we have moisture, and we're gonna actually solve the equations as a perturbation series and get what we will get from this perturbation series expansion. So now we get a solution where omega is equal to the phase p times the wave number. We're not gonna pay a lot of attention to that. And then you have three imaginary terms that lead to instability. You have this MVI term, which is in blue. This is gonna be our moisture vortex instability term. BCI is gonna be baroclinic instability, which is essentially what I showed in the previous slide. And then this BMI term, which is in purple and pink, this pinkish purple is going to be a baroclinic moisture vortex interaction term. So when you add convection, moisture and convection feedback, so this tau c, you no longer just have one instability, you now have three terms. And this is going to be one of the important things, all right? So you don't longer have this BCI term only, we have three things. And we're going to analyze how these three things look together. So this is going to be the next slide. We're going to assume that tau c is 6 minutes. This is actually like an incredibly short time scale compared to what we think happens in observations, which is more like on the order of hours. But this is still instructive enough. Here in the four panels, the positive, this is westerly thermal wind in the top, and then the bottom is easterly thermal wind. But otherwise, the panels are the same. The contours is the baroclinic instability. So the baroclinic instability is just shown as contours. And then the shading shows you moisture vortex instability as red, and then decay in blue. And then the BMI, which is the baroclinic moisture vortex interaction, is shown in the right. So here we see that generally moisture vortex instability strengthens as you increase tau c. You see red here and a lot of red here. So we see that in easterly shear, but like we see here, you see a lot more intensification of moisture vortex instability compared to westerly shear. That's going to be one thing. The BCI term, you don't see a lot of change. They're pretty much the same. And then the BMI, which is the interaction between baroclinic and moisture vortex instability, tends to weaken baroclinic instability in easterly shear, which is this D panel down here. So you see a lot of blue, which is weakening only where you see baroclinic instability. So the take-home message is the following. When you increase the convective adjustment timescale, which essentially increases the moisture, you see an increase on moisture vortex instability, essentially at the expense of baroclinic instability. So you see the strengthening here in red and a weakening here in blue. And it's very pronounced in easterly shear, and a lot weaker in westerly shear. So now we're going to look at the full solutions and compare that to that approximate solution that we saw before. This is the solution for tau c equal 0.1 hour. Again, baroclinic instability is in contours, and then the full solution is in shading. So when tau c is 0.1 hours, they look exactly the same. So convection adjusts so quickly that you can barely notice that there's anything added in there. As you increase your convective adjustment timescale, you see that there's now instability growing outside of the regions where you see baroclinic instability, which again is the regions where you see the contours. So now you see growth in these regions out here and out here. It's a lot more pronounced in the easterly shear than in the westerly shear. All right, and as we increase tau c to 2 and 4 hours, that becomes even more pronounced. So you see now a lot of growth in the 4 hours region outside of baroclinic instability, especially in easterly shear compared to westerly shear. And if you look at inside the contours, you see that the baroclinic instability has weakened a lot. So if you compare this last panel to the right to the first panel, you see that the oranges and yellows are a lot softer than what you see in the first panel. So what does this mean? So let's give a comparison. So let's compare, for example, this. Let's go to this 4 hours here. Let's compare the structure of shear. So this is wave number 8 in westerly shear, and let's compare wave number 8 in easterly shear. So we're going to look at exactly the mirror images, the same location in terms of thermal wind, so 20 meters per second, wave number 8. But one's going to be westerly shear, and then the other one's going to be easterly shear. But otherwise, they're going to be the same. So when we look at westerly shear, so this is the panel that we're looking here, you see a low at the surface, and you see a little bit weaker, but you still see some westward tilt with height. So this still looks like baroclinic instability. Westerly shear, again, winds are becoming more westerly with height. So you still see a structure that's qualitatively consistent with baroclinic instability. You have the tilt that you would expect to see. But when you look at the easterly shear, so exactly same location but opposite shear, you see a dramatically different structure. You see a very strong surface cyclone or an anticyclone, a mid-level low, and then essentially nothing in the upper troposphere. So we're seeing that we're changing the structure of the system from a baroclinic instability system when their convective adjustment is 0 to a system that when convective adjustment is non-zero, it completely looks different from baroclinic instability. It looks more like kind of like a tropical depression to some degree, mostly a surface low. So what does this mean? Why are we getting here? Why do these two shears give you such different structures? So let's think about that before we conclude. So the thermal wind is actually the main cause of what's going on. So if you didn't, if everything else was a bit terse, like this is kind of like the neat conclusion here. So if you have a surface cyclone, so here's a low, and you have a cyclonic circulation, and you have a thermal wind that is westerly, so you have easterlies at the surface, we're just going to assume that the wind just reverses direction. We're not going to assume, that's kind of like easier to think about. And we have westerlies on top, and I'm more like the mid-latitudes. You have that the wave would propagate to the west, and the thermal wind, so the surface easterlies would actually push the moisture in the same direction that is pushing the wave. And this pushing, so you will see that the moisture is being pushed westward in the same direction as the wave. That tends to favor this kind of configuration where the precipitation kind of occurs in quadrature with the low, and it turns out that this favors baroclinic instability. This favors this kind of configuration. However, when the shear is actually easterly, you have westerlies near the surface and easterlies aloft. But your low is still propagating westward because Rossby waves like to propagate west because of the beta effect. So you have a westward propagating disturbance, but now the thermal wind is actually advecting your moisture towards the center of low pressure. So in one case, your thermal wind is actually advecting the moisture away from the low pressure center, and the other one is actually advecting it towards the center of low pressure. And this causes that in the easterly thermal wind, you get convection co-located with the center of low pressure, which actually intensifies the vortex through vortex stretching. Whereas in the other case, you don't get that. So instead, the baroclinic instability will be the main mechanism to have this growth, whereas in the easterly shear, you get these vortex stretching mechanism be the predominant mechanism. Now, last but not least, I wanted to compare the vertical motion with the simulated monsoon depressions. So here in the top panel, the red, ignore the little tiny lines, just focus on the black line, the blue line, and the red line. The blue line is ascent due to diabatic heating, so this is convectively driven ascent. So you see ascent here, where it is positive. The black is the total ascent, and then the adiabatic lifting is in red. So the adiabatic lifting is just large-scale lifting from like the omega equation without the heating component added to it. So you see that in monsoon depressions, the convection is to the east of the adiabatic lifting, or conversely, you can say that the adiabatic lifting is to the west of the convection. So when you look at the wave solutions that we had, we see the following. So here, the blue again is the diabatic ascent, and then the pink is the adiabatic ascent. The total ascent is in purple. We see that when the shear is westerly, these two things occur in phase. So you have the adiabatic lifting and the convection occur in the exact same location, which actually is favorable to for baroclinic instability. But in easterly shear, you see the same shift that you see in monsoon low pressure systems. You see that the adiabatic lifting is actually shifted towards the west of where you see the diabatic heating. So what does this mean? What is the main conclusion of this? So what this means is that if you add prognostic moisture and convection, so you make your region humid and you make your precipitation be a response of the humidity of the troposphere, you will find that in regions of westerly shear, baroclinic instability is actually favored. But in regions of easterly shear, this in-phase component of the moisture and the low pressure actually favors moisture vortex instability instead. So you just have one instability in westerly shear and then a different instability in easterly shear. And what this means is that, well, we all knew that baroclinic instability is favored in the mid-latitudes. The shear is westerly. Probably even in the summer when you have a lot of humidity, that's probably still true. But in the tropics or in the outer tropics where UF is quite significant, like in the Asian and African monsoons, it seems likely that baroclinic instability is not what actually drives monsoon low pressure systems or African easterly winds. Instead, it might be this moisture vortex instability. And with that, I conclude. It seems that baroclinic instability weakens in easterly shear when moisture is prognostic and the troposphere is humid. Number two, moisture vortex instability seems to take over as the main instability once you kind of add more humidity and increase the convective timescale. And then, furthermore, monsoon lows, maybe even African easterly winds, is a little bit harder to say because the Rossby number is a little higher in this region. It's possible that these are driven by moisture vortex instability and not really baroclinic instability. But last but not least, I really wanted to end with a major caveat. This is a really simple model. And this is analytical. So there's a ton of caveats to what I just did, just QG approximation, just the type of assumptions that I'm making. More work really is needed to really elucidate what's going on in these regions. Like, this is just a suggestion. This result just suggests that maybe baroclinic instability is not the main mechanism. That seems to be what's going on in observations. The theoretical results seem to be more consistent with a moisture vortex instability mechanism, but beyond that, that's as much as I can say as to what is going on here. More work. We really need more work, more observations, more simulations, and things to tell us what's actually going on in these regions. With that, I conclude. Thank you for your time. I'll take any questions for those of you that have any. If you want to chat in more depth about the paper, here's my email. The paper is still it hasn't been accepted yet, but it should soon. It's been revised. It's gone through the peer review process, so I expect it to come out maybe early next year. But here's the title of the paper for those of you that want to see it, want to check it out whenever it comes out. Thank you.
Thank you, Ángel. That was really interesting. So we will go ahead and open it up to questions. We will begin with any students. Do any students have any questions for Ángel? Okay, we'll just go ahead and open it up to everyone. So go ahead, Dan, with your question.
Thanks, Ángel. That's a great result there. In terms of the dynamical mechanism for these moisture vortex, is it just that the phasing of this that you get a divergence, a convergence at upper levels that then projects onto the potential vorticity itself, so that the dilution, I guess stretching effect of, and so forth ends up amplifying? Is this why this becomes unstable?
Yes, that's right. So this is essentially like a circulation convection feedback, where you have the convection co-located with the surface low, and then that stretches the vortex. But then the advection, temperature and moisture that the circulation brings in more moisture for more convection to happen. So you do need that phase in relationship, but it's really a moisture circulation feedback that happens.
It's interesting that this is for the higher wave numbers as well. So the lower wave numbers, that what kind of kills the real wave number instability there? So
it's interesting, because what happens is that in this case, I checked this when I was a postdoc a while back. So in that case, when the wave is very large, it moves very quickly. And so you have more gravity wave-like behavior. You don't get geostrophic adjustments. So the vertical velocity profile becomes less favorable for having the vertical velocity occur near the center of the low. So essentially, it's kind of like it's moving too fast. Essentially.
Yeah, I see what you're saying. That makes sense.
Yeah. Well, I say John has a question.
Yeah. Thanks, Ángel. Great talk. Very, very interesting stuff. I about so many aspects of it. One is that the Sutcliffe development theorem applies at degrees north and south. I like the presence of the thermal wind advection of vorticity in both of your spin-up terms. That's exciting. I was wondering about the if there's any importance at all to thermal wind advection of vertical gradients of moisture, in the sense that you can get differential moisture advection that can alter the stability in different locations. And it seems to me, just at a quick thinking about it, westerly shear would probably tend to induce a moist PV reduction over the cyclone center, whereas easterly shear would do the opposite. Is that possibly embedded somewhere in the equations and just not explicitly described, or am I on the wrong track?
No, you're exactly on track. So this is what so the schematic that I made. This is a two-layer model, and all the moisture is in the lower level.
Mm-hmm.
You don't get this differential moisture advection by the thermal wind. You instead have like the lower level component of the thermal wind driving everything. But in reality, you probably do have a differential moisture advection. And the way that I have it in the paper that I didn't describe it in full detail here is that if you get like a moist PV, the one in easterly shear, you get higher moist PV. So you're essentially like pumping moist PV in the easterly shear, and then the westerly shear, you're actually destroying it.
Okay, yeah, that's consistent with the Bennett's and Hoskins. I think when you do the full derivative of the moist PV, you find that interesting adiabatic term, and it fits right into your theory. Okay, right. That's really interesting. Okay.
So interestingly, and I'll throw this pebble at your way. It seems that moist PV generally describes both the dry and moist regimes, and it's generally the equation that describes the dynamics of the whole wave. It's not moist static energy nor QGPV. It's the moist PV.
Oh, that's very interesting. Yeah, that's great. I'm going to read your paper. I can't wait to see it.
Cool. I'll send it when it's accepted. See Thanks. Dan again?
Yeah, sorry to I don't mean to dominate here. I was wondering, could you put up the equations for the prognostic equations for the moist enthalpy?
Yeah. Okay. Yeah, this one. So the third one.
Yeah, and remind me what the beta terms are here.
So the first right-hand side term is moisture advection by the Baroclinic wind anomalies. Okay. So, and then the second one is actually like moist static energy advection by the barotropic wind anomalies. The third term is actually moisture advection by the thermal wind. So this is the term. This is, I think, the term that John was referring to earlier. Okay. And then this last term is actually really vertical moist static energy advection by the convection.
Got it. Okay. So the beta Q and beta T terms are those imposed like mean state, or is that?
Yeah, that's the mean state. Yeah, if you the monsoon mean state, I essentially did it for like a monsoonal, a South Asian and an African monsoon mean state, and then beta T and beta Q are just moisture and temperature gradients in beta units. They're like in vorticity gradient units. So I just rearranged the terms so that they're comparable with regular beta.
Yeah. Okay, got it. Thanks.
Yeah.
Very, very nice work. All right, well, that's really cool.
Cool. Thanks. Glad you like it. Any other questions? I see Brad.
Ángel, could you go to your? I think it's the last slide, your conclusion, where it goes back to the observed. Yeah. So we were talking before where there might be some apparent westerly tilt with height, but it sounds like your easterly solution is this maybe exponentially decaying part of it, right? With the peak at the bottom.
Yeah. So it kind of decays with height, essentially, is the easterly solution. Yeah.
So could you get some kind of mixed modes where, Because there does seem to be part of it that still tilts westerly with height.
So yes, that's right. So essentially what I described here is kind of like the two edges of the spectrum. You can have like just pure baroclinic instability and then pure moisture vortex instability, but anything in between is also gain. So you can have some kind of mixed baroclinic moisture vortex instability also being explaining. Now I'm gonna add that like the tilt in this figure has to be eastward, not westward. So it's actually tilting the wrong way. So that is part of the issue. But the structure is more consistent with moisture vortex than baroclinic, so it might be more that way than in the other. But more work is definitely needed to confirm that. And also, like barotropic instability could also be playing a role, and I just didn't look at that either. So there's definitely a lot more to look at.
That was something that at the beginning I don't think I understood. You were saying in the easterly regime you have to have easterly tilt with height, but to have baroclinic instability, right?
Yeah. So in easterly you have to have the tilt with height has to be eastward.
And this figure that's from some reanalysis, or is that still a simple?
No, this is the GFDL, the
right.
AM4 model. Yeah, it's not reanalysis.
So couldn't you get something from? You could have a component of it that is this typical mid-latitude westerly tilting with height baroclinic instability, and I don't know why. Is this is limited to like the easterly shear regime? That's where you're doing the analysis, or?
Yeah, that's right.
I don't understand.
Yeah.
Okay.
So it's in the monsoon. It's in the conditions of the South Asian monsoon in the summer.
Okay.
Yeah. I see more hands. I see Karimar next.
Yes. I do have one. I mean, maybe it's not directly related, but I'm just curious to know what would be like the relationship, or if there's a direct relationship with the intensity of tropical cyclones or the tropical cyclone activity. Like we can just use this like to kind of predict this kind of phenomena or something, or.
So you hit the nail on the head. You hit sorry, I like took completely off here. But yes, you're absolutely right. And one of the things that we intend to look in the future in our group is to see if, for example, this moist potential vorticity framework could be insightful in one way or another. But yeah, it is interesting that the structure is kind of reminiscent of tropical depression. Right now, I cannot give you anything in addition that it kind of looks that way, but it does maybe give some kind of suggestion that there might be some relevance to tropical cyclones, but we haven't looked at that yet. But it is a really interesting question, and I think that it will be an interesting direction of future research. Does that answer your question?
Yes, thank you.
Okay, I see Greg is next.
Yeah, a very nice talk. What I'm trying to understand here is there a range of unstable modes of horizontal wavelength, or are you just looking at one? Because I'm wondering if there's a most unstable mode that would represent a convective plume, for instance, versus the wave itself.
Yeah, so there, like you see in the diagram here, it seems like the most unstable mode for the two-layer model is it seems to consistently be between wave numbers 5 and 10, even as you crank up as you tune the parameters. So it seems to like to remain close to the wavelength of baroclinic instability, even as baroclinic instability weakens. So there's definitely some kind of anchoring to some kind of synoptic scale, regardless of what happens. Can you repeat the rest of the question again? So I see if I can.
Well, what I'm wondering is why doesn't a thunderstorm, for instance, show up as the most unstable mode in this if you have conditional instability?
So I think it's because, so it's a good question. I think it's because it's convective adjustment. I think it might be because of the convective adjustment. Oh, and by the way, this is, I think I'm getting to the point of this. I didn't discuss here the gross moist stability. So if your gross moist stability is 0, exactly 0, you do get some kind of like ultraviolet catastrophe, unless you, for some specific conditions. But if it's just slightly greater or smaller than 0, it's not. So here I'm assuming that the gross moist stability is not really exactly 0. So this is something that needs to be addressed later on. So you do see some kind of like thunderstorm scale stuff happening if your GMS is really close to 0, or exactly 0 more.
This is a little reminiscent of the wave-cisc theory that, from 20 years ago.
Yeah.
In the sense that the most unstable mode would have turned out to be this catastrophe, or whatever you call it, the ultraviolet mode or something. And they spent a lot of time trying to tweak the cumulus parameterizations to get the right scales to pop up. And to some extent, you can ask if, to what extent, the results are dependent on the cumulus parameterization that you're using, the adjustment scheme, more or less.
Yeah. And there's definitely more work that needs to be done, but I think that generally it seems that using a convective adjustment, some kind of like buoyancy thermodynamically based scheme seems to do better. A lot of this is kind of like based on a lot of what moisture mode research has been on in the MJO and other tropical stuff. So that's kind of like where I'm kind of like picking it up from. Generally, there's no generally ultraviolet catastrophe in those. But yeah, I do think you're right that this would be sensitive to the type of scheme. I don't know how much would need to see, but I would guess that different schemes would lead to different results one way or another. Yeah.
Okay, thank you.
See Mel.
Yeah,
Next
hi,
question.
Ángel. Yeah, really cool talk. Thanks for doing this. I had a context question just about tropical dynamics in the extratropics for westerly shear. There's the sort of Baroclinic instability idea exciting one single mode, but in reality we see that the tilt of the anomalies with height varies and becomes more vertically stacked with time, and so that introduced the idea of non-normal growth and sort of transient amplification in addition to baroclinic instability. So I'm just wondering, in the tropical community, is there a similar sort of tension between those two ideas as well, or not?
I think that there is interest. This could be me being maybe out of pace with the community, but I think that there is interest in learning more about transient growth of systems, but because kind of like what are the main instabilities hasn't been like a fully solved question in the tropics. A lot of these, like moisture-vortex instability is pretty new, and moisture mode instability is fairly recent. I think that in general we're quite a few steps behind still into kind of like addressing like more transient development. But I would probably guess that all the growths that you see are transient, like even easterly waves. Like even though the regression structure looks like this, it doesn't look the same the whole time.
Right.
But I will say that, for example, and the analysis of monsoon depressions, it never really has the tilt that is necessarily to satisfy baroclinic instability. Like if you look at a composite life cycle, it never really has that structure. It's almost always upright, but the depth of the upright structure does change. I think in African easterly waves, it does have different tilts. So for African easterly waves, it's a little bit more difficult to draw any conclusions. The mean state is also a little bit more complicated. And you also have Africa then exiting into the Atlantic, etc. So there's more complexity happening there. But generally speaking, my understanding is that we know that transient growth is what happens, but that hasn't been fully characterized for most of these waves. But maybe somebody else can chip in and add that. But that seems to be my understanding.
Yeah, cool. Like definitely instability is very important. So that makes sense that would be the way the research is progressing. Cool. Thanks.
Yeah. Cool. Any other questions? Cool, almost exactly at the hour. At 4:30.
Yeah, thank you, Ángel. That was a great presentation. If nobody else has questions, then that will be it. So thank you again, Ángel, for the great talk.
Great, thank you. Thank you, everybody, for attending.